Welcome to lecture 6 of our system protection course. Previous lecture, in the lecture number 5, we talked about the DC offset current, how DC offset current is being produced during the fault, and also how it affects the saturation of the CT core, and therefore how it affects the protection system as well. We discussed all these things, and also we introduced we talked about the voltage transformer, because voltage transformer, the ratio is very high because it's around 400 kV is to 110 volt, or more than that, or 220 kV is to 110 volt. The ratio is very high, and therefore if we'll take the voltage, line voltage, directly and feed to the transformer, then the design of the transformer itself will be very bulky and costly. And in order to avoid that, we use the capacitors which are coupled in order to make, or in order to design, the potential divider, and through that the small voltage, it's around maybe some 2 to 2 kV, 3 kV, around that voltage is fed to the transformer itself. By that way we avoid the bulkiness of the transformer in design and the cost of the transformer. So today also we'll discuss more about the voltage transformers, the transient response. In this lecture we'll talk about the response of the voltage transformer, and we'll talk about the ratio error and phase angle error of the voltage transformer. Then we'll illustrate this using some examples. So we'll see now. So we'll see how CCVT, that is capacitor coupling voltage transformer. In fact, CCVT is capacitor coupling or capacitor coupled voltage transformer. So CCVT in power line communication, because we use the capacitance in the CCVT, so that is in fact useful, very useful, to trap the communication signal which is being transmitted through the transmission line. So we'll see it. So you can see here, this is one CCVT where we have three capacitances. We have three capacitances are in fact you can see here three capacitances connected in series to make an potential divider. This is 1, 2, and this is 3, right? So, and one of the capacitor is feeding to the potential transformer, right? Now here we can see that already we know there is a compensating reactor which is very essential, very essential for for neutralizing the effect of capacitance drop, and it is very essential for that. And we have this is also called tuning reactor, and we have a drainage reactor. You can see here drainage reactor. Why it is essential? We can see here why it is essential. Now suppose this is your transmission line to which this end of the capacitance is connected, and the communication signals which are being transmitted on the through the transmission line are of high frequency, so they are called RF signals. Okay, so they are called RF signals, and they are of high frequency in nature, and our power system signal is 50 hertz, whereas they are in kilohertz. RF signals are megahertz, right? So when the frequency is very high, what happens? So these capacitances, in fact, these capacitances, they provide a low impedance path, right? They provide a low impedance path to the RF signal, not to the power signal. So we have two signals now in the transmission line. One is RF signal and other one is your power signal. Okay. So this RF signal, because it is high frequency, so to RF signal only, this capacitance provide, these three capacitance provide a low impedance path, right? And therefore it is very easily, it can be transmitted directly to this wave trap. This is called wave trap, and where the tuning pack is there. Okay. And through the wave trap, the signal is being transmitted to the control centers, right? So now this wave, these RF signal waves will be easily transmitted through these capacitances, and here we have a drainage reactor. Why it is there? Because this reactor provides a high impedance to the RF signal, because as the frequency is very high, the impedance of this reactor will become very high. This reactor also provides high impedance path. So therefore the signal will not pass to the ground, it will pass through the wave trap. Okay. Now why this reactor will provide a drainage path to the power signal. Okay. So whatever power signal will come through this, it will provide a drainage path to the power signal, not to the RF signal. So by this way, these capacitances are very useful in order to trap the RF signal or the communication signal in the power line carrier communication. So now you can see here uh, in the secondary side we have ferroresonance suppression circuit, which in fact helps us to suppress the ferroresonance. So we'll not talk much about the ferroresonance. Okay. Now we'll see the transient response of capacitor coupled voltage transformer. How the transient response looks like. Okay, let us see it. So this is the equivalent circuit. Even we can say that modified or simplified equivalent circuit, uh, where VTH is your Thevenin voltage and this is your equivalent impedance provided by the capacitors. If we have two capacitors, C1 and C2, and omega L, J omega L is the impedance provided by the tuning reactor. Okay, so how the transient response, because this is RL circuit, and how the transient response will look like. So if the transformer is considered ideal, then we can write the equation for the response of this transformer very easily, right? So what is response means? Response means we need to find the voltage, in fact voltage across this RV, okay, or we can say VR. So simply by writing the equation for this RL circuit we can find this, right? So if we write the equation for RL circuit, we can write this equation dV by dt equal to R di by dt plus 1 by C equivalent. C equivalent is this, right? This is your C equivalent and this is L. So 1 by C equivalent I plus L d square I by dt square, right? You can write this very easily. This is because simple RL circuit. Now if we'll write the equation for I, then I can write d square I by dt square plus R by L di by dt plus 1 by L CQ I equal to 0. So this is, I can write this from this equation. I can very easily find out the response of I, right? If I'll know IT and I'll substitute IT here in this equation, then I can find the response for VR. What is V is mentioned here, that is nothing but VR, right? Okay, so I can find the response for VR very easily, right? So now I can write the response very easily, and by finding the response of VR, if I'll plot this voltage, or say the fault voltage waveform under CVT transients, so I can say here, just let me erase it. So I can see that the transient response, suppose the fault occurs at 0.4 second here at this point, okay, at this point, and we'll get the normal voltage up to 0.4 second. Then after 0.4 second, the voltage goes down very. Actually, in fact, it should be 0 ideally, but because of the transient response, it actually uh, becomes like this, right? So we have two responses we have plotted here. You can see here with CCVT and without CCVT. So without CCVT, in fact, the magnitude is less as compared to with CCVT because of the presence of the capacitance. Okay, so this is your transient response, and if sometime your transient response persists for more time, it may cause that your sometime it causes that your relay may not operate properly, it will maloperate. Okay, so let us see the classification of CCVT. So we have two classes of VT, okay, CCVT. One is class 1 CCVT and class 2 CCVT. So how we'll differentiate or distinguish between these two? That is based on the maximum error and maximum phase angle error, maximum ratio error and maximum phase angle error. So for class 1 CCVT, maximum ratio error persists, that is plus minus 1%, and maximum phase angle error is plus minus 40 minute. So what is plus minus 40 minute? So 40 minute, if we'll say convert it into radian, that is, I can say that 1 radian is equal to 60 minute. So 40 minute will be equal to how much? It will be equal to 1 degree. 1 degree is equal to 60 minute, and 40 minutes similarly I can convert it 1 by 60, 1 by 60 into pi by 180 into 40 radian, right? So this will be this is in fact the conversion of degree to minute, and if we'll convert minute to radian, this is the way we convert from minute to radian, right? Okay, so therefore your maximum phase angle error for class 2 VT or class 2 CCVT is 80 plus minus 80 minute, and class 2. For class 2 CCVT, the maximum ratio error is plus minus 2%, right? So that means based on the ratio error, it is classified class 1 and class 2. For class 1, it is 1%. For class 2, it is 2%. Okay. Okay, so now we'll see tutorial on voltage transformer. In fact, we'll discuss the ratio error and phase angle error through these tutorials, and you will understand very easily through the examples, right? First example is we need to design a CCVT, right? We need to design it for a 132 kV transmission line using the following data. What are the data given here? One is resistive burden, that is 150 volt ampere, which is nothing but the burden of the relay. Okay, the burden of relay. Okay, and frequency deviation to be subjected is delta F, that is equal to 3 Hertz. That means it can bear up to frequency deviation of 3 Hertz, right? That means based on that frequency deviation, the phase angle error, that is beta, equal to 40 minute. So we'll see what is phase angle error. When the frequency deviation occurs, in fact, the resonance between the capacitance and the tuning reactor, it deviates, and because of that there is a voltage, there is a phase angle difference between the voltage across the relay, okay, across the relay, and voltage that is in fact fed in the primary circuit. Okay, so that angle difference is known as the phase angle error. So consider four choices of voltage. So considering these four choices of voltages, V2 as 33 kV, 11 kV, 6.6 kV and 3.3 kV. Transmission line voltage is 132 kV, it is given. And the standardized voltage VT secondary voltage is 110 volt. Okay. Now we need to design this voltage transformer. What we need to design, we need to find the capacitance values and tuning reactor values, right? Reactor values. So we need to find these two things, capacitor value and tuning reactor values. So let us see how we'll proceed. So this is your CCVT, where we have used two capacitances in series as potential divider, right? That is C1 and C2 here, C2, and V2 is being fed to the transformer primary circuit, and L is your tuning reactor. So we need to find C1, C2 and L. Okay, so how to find this is your RB. Now we need to transfer this RB to the primary side so that it will become a single circuit and our analysis will be becoming easier. So let us transfer this to. So now after transferring RB to the primary circuit and also simplifying the capacitance and reactor in the circuit, we can see here we'll get a simplified circuit, simply RL circuit, and as RB dash is transferred to the primary side, so RB dash will be RB dash is A square RB, right? Okay, so now what will happen? So for voltage deviation, during voltage deviation, this is during voltage deviation, how it will affect, not voltage deviation, during frequency deviation, this voltage across the capacitance, across this capacitance and the inductance will deviate, right? So, and we know under nominal frequency, that is omega naught. So we'll see that we know that what is that? The uh, tuning reactor, that is j omega L, is equal to 1 by j of omega C1 plus C2. So we know this, right? This is at nominal frequency, right? Now if the frequency deviates, then what will happen? These voltages will vary. The voltage across the L and the voltage across the C capacitance. So now because these voltages vary, and we have represented here the voltage across the reactor as VL and voltage across the capacitance as VC. So as it is vary, we'll see that there will be a certain voltage drop. So now that voltage drop I can write it as delta VL minus delta VC. That is equal to nothing but J of I times D by. So how I can find this? Can you guess how we'll find? We'll just find by taking the uh, derivative and also evaluating it at initial conditions. So that is Taylor series expansion, right? Simply by uh, using the Taylor series expansion, we'll find this expression, right? So this is nothing but, so ji is taken common outside, and I'm taking the derivative of first term, that is the voltage drop across inductance, and the derivative of the voltage across the capacitance, and that is evaluated at omega naught, both of the terms. So if we'll take the derivative of omega, it will be, with respect to omega, it will be L, because we are taking the varying quantity here as omega, right? So therefore I am taking derivative with respect to omega. So when I take derivative with respect to omega, it will become I times L. The first term, if we'll take derivative, it is L, and second term it will be minus of 1 by omega square C equivalent. So it will become plus here, and 1 by omega 0 square C equivalent, because we are evaluating this whole term, the derivative term, at omega 0, right? So by substituting omega 0, we'll just get the term L plus 1 by omega 0 square C equivalent into delta omega. Okay, now this is your expression. Okay, so this is your expression for, it is evaluated at omega naught. Okay. Now we know this, that omega naught square is equal to 1 by LCQ. Now substituting this in the previous equation here, in this equation, so we'll find, just substitute 1 by LCQ, we'll find this is in fact LCQ, okay, C equivalent, okay. So by substituting, we'll find delta VL minus delta VC, which is the variation of the voltage drop because of the frequency deviation, that is nothing but equal to I times L plus L into delta omega. After substituting 1 by LCQ here in the first equation, we'll get this term, right? That is I times 2L delta omega. So now what is phase angle error? Well, we can see it here. So this is your voltage across the burden, across the relay, and this is your voltage. VTH is the voltage which is fed across the primary side. And now if there is some voltage deviation between VL and VC, if they are not equal, if the frequency is varying, because the capacitance and reactors, they are tuned at nominal frequency. If the frequency varies, then there will be a voltage difference. Now because of that frequency deviation, this voltage drop happens, VL minus VC. This is nothing but equal to delta VL minus delta VC, right? So now we can substitute here. So now beta, how we can define? So I can write here tan beta is equal to nothing but VL minus VC magnitude by VR magnitude. So I'll get, so VL minus VC is nothing but this is your delta VL minus delta VC, right? So therefore it will become equal to 2Li delta omega A square RVI. Okay, so that is nothing but twice of I will cancel out, twice of L delta omega by A square RV. And we know that this tan beta, because beta is small, phase angle error, sometimes it is big, it is very small. So therefore I can write tan beta is nothing but approximately equal to beta, and hence from the we can write percentage phase angle error beta is equal to twice of L delta omega by A square RV into 100. Okay, this is a percentage phase angle error. Okay, so your phase angle error is it given in your question? Phase angle error is 40 minutes, right? It is given. So using this equation, the value of L for different values of V2 is found. Now let us consider each of the voltage, because we have considered 4 choices of voltages. Here in the question we can see we have 4 choices of voltage: 33 kV, 11 kV, 6.6 kV and 3.3 kV. Now we'll consider the 4 choices individually. Okay. Now let us consider first V2 equal to 33 kV. So after considering this, so we'll see that, so you know that your burden is 150 volt ampere, and which is nothing but equal to 3V2 square RV dash. Okay, and RV dash is nothing but A square RV. So if we'll substitute if we'll substitute the value of V2 here, we'll find RV dash value, right? And then we can find, by substituting this RV dash here in this equation, because we know beta, L, delta omega, everything. So now by substituting RV dash in this equation, right? So we'll find delta omega. Sorry, we'll find delta omega, you know, if we'll find L, okay? Because delta omega we can find very easily, because there is a frequency deviation already given in the question, that is 3 Hz. So now I can find delta omega, that is 2 pi delta F. And then by substituting all these values, I can find, so beta also will calculate 40 minute is equal to 0.01164 radian, right? By substituting these values, we can find the value of L. So L is nothing but beta RB dash. RB dash is nothing but A square RB by twice of delta omega. Just by substituting the values, we'll find the L value as 6722.2 Henry. Okay. And now substituting this L value in the value of omega 0 in the equation of this, omega 0 square is equal to 1 by L C cube. Omega 0 we know, L we know, so C equivalent we can find out. C equivalent is nothing but C1 plus C2. So then C equivalent is found to be 1.51 into 10 to the power minus 3 microfarad for the voltage of 33 kV, right? Now we'll consider similarly voltage of 11 kV. Okay, similarly we'll go for calculating RB dash, then substituting RB dash, we'll calculate L. Then after substituting L in the nominal frequency equation, nominal frequency tuning equation, we'll find C1 plus C2. So L is found to be 747.2 Henry for V2 equal to 11 kV, and equivalent capacitance, that is C1 plus C2, is found to be 1.36 into 10 to the minus 2 microfarad for voltage level of 11 kV, which is fed to the primary side of the Vt. Now if we'll consider V2 equal to 6.6. In the same fashion, we go ahead for calculation. We found RB dash, then L is found to be 269 Henry, and then C1 plus C2 is found to be 3.77 10 to the minus 2 microfarad. Okay. So then another choice we have is V2 equal to 3.3 kV. So for this also we found RB dash, then L is found to be 67.25 Henry, and C equivalent, that is nothing but C1 plus C2, is equal to 0.151 microfarad. So now we calculated the values of L and C1 plus C2 for all the four choices, and now we'll summarize all these four choices. So this is your voltage level, four choices given, four choices, and the calculated values of L and C1 plus C2 in Henry and microfarad is tabulated here. So what we are observing here, for higher values of the V2, the value of H is in fact very high. This is here we can see 6722.2 Henry. It is very huge value in fact, and if we'll design the inductance for this or manufacture the inductor for this, it will be very huge and very costly as well. And the capacitance value is also decreased as the voltage level is increasing. If we'll consider the minimum voltage level, that is 3.3 kV as V2, then your L value is 67.25 Henry, and the capacitance value, it is fine, the 67.25 Henry, but the capacitance value is very high, 0.151, right, microfarad, which is also very high value, and if we'll design the capacitor, it is very high. So therefore, out of these choices, we can see, let us see the 6.6 kV voltage level, for which the L is 269 Henry, and the capacitance is 0.0377 microfarad, and for 11 kV it is 747.2 Henry and 0.0136 microfarad. Out of this choice, the most suitable choice is this choice, that is 6.6 kV, because if we'll see because we want to reduce the inductor size and capacitance size as well, both, and this is the most optimal size for inductor and capacitance or capacitor, right? So we can consider 6.6 kV, for which the L is 269 Henry and 0.0377 microfarad capacitance values. Now the equivalent capacitance is found C1 plus C2. Now how we'll find the C1 and C2 in a segregated manner, individually C1 and C2, how we'll calculate? So a compromise solution is necessary, and let us select V2. So V2 is selected. For that we found the L and C1 plus C2. And now the question is how to find C1 plus C2 is given, C1 and C2 individually. Now L is given here, right? So L is your 269 Henry, and C1 C2 is given here 0.0377 microfarad. And now if we'll see the equation of current, So if we'll go back to your equivalent circuit, here we can see here uh, because the current flowing through this is negligible, so I can say that the current passing through C1 and C2, they are equal approximately. So I can write here that I can write that IC1 is equal to approximately equal to IC2. Okay, so from this equation I can write C1, sorry, the voltage across C1 is V minus V2. Okay, this is your voltage that is equal to C2, voltage across C2 is V2. Okay, so now I can write this equation as C1V equal to C1 plus, sorry, C1 plus C2 into V. Okay, now I can write, sorry, into V2. So I can write this as V by V2 is nothing but C1 plus C2 by C1. Okay, so from this we can write this equation V by V2 is equal to C1 plus C2, and we know V is the nominal voltage, given voltage, that is 132 kV, that is line to line. If we'll convert it to phase voltage, it is 132 into 10 to the power 3 by root 2, and V2 also we considered here. From this, V2 is 6.6 kV. Now substitute this here, 6.6 kV. So we know that your V is given, V2 is given, and C1 plus C2 is given, and we will find C1 from here, from this equation, right? So after finding C1, we can find C2 as well. Okay, so similarly C2 can be found from this equation. So C1 is found to be, it is found to be 0.0033 microfarad, which is suitable choice, and we can design a very nice capacitance, right, for C1. And C2 also found to be 0.0344 microfarad. Okay, so this is how we can design a CCVT, or capacitor coupled voltage transformer. Okay, so the transformer here really assumed ideal, and therefore the ratio error is not at all considered here. So now let us consider these aspects, ratio error and phase angle error, in the next example. Okay, this is the figure given here. This is the CCVT given to us, that is C1 and C2 is given here, C1, C2, and RL is given, and we are considering here the exact equivalent circuit. Rather unlikely, in the example 1 we considered an ideal transformer in that CCVT, but here we are considering a practical transformer, considering R and L, that is resistance of the winding, and L is the is the leakage inductance of the winding, and Xm is considered here. Xm is your magnetizing reactance, and Rm is your core or core loss resistance, that represents the core loss. Already you have studied these things in your Mason's course, and in fact Cm is one of the capacitance which is required in order to tune again. That is, we can say that is Cm is your compensating capacitance. Okay. So let us see the question. The equivalent circuit of the CCVT as shown in the figure below. The values of C1 and C2 are 0.0018 and 0.0186 microfarad respectively. Compensating inductor has a resistance of 4620 ohm, right? So that is the resistance of the compensating inductor. This in fact you can say the compensating inductor is included here. Okay. Resistance of this ohm, Xm of the Vt referred to 6.6 kV side is 1 mega ohm. That is Xm is referred here to the primary side. That is 6.6 kV here is mentioned across the C2. That is 1 mega ohm, right? So this is very huge value. And core loss is 20 watt. In fact, using this component we'll find the Rm, right? Per phase, this is per phase is given, and VA burden is 150 volt ampere. This is we call relay burden. Okay, and find the appropriate choices of L and Cm. So how we'll find the choices of L and Cm? This is the first question, and second question is find out the nominal value of line voltage. Okay, that is V here. What is the value of V? And if the frequency drops from 50 Hz to 47 Hz, 50 Hz your nominal frequency, and if your frequency deviates by 3 Hz, what would be the values of ratio and phase angle error? So we need to find here ratio and phase angle error. Ratio error is represented as alpha and phase angle is represented as beta. Then fourth question is what would be the ratio and phase angle error at the nominal frequency? Okay, so let us see this, and all these quantities are really compensating all the values of the resistance reactance because of the compensating capacitance and compensating reactor here. Both this capacitance effect in fact compensates Xm, and this in fact this L is really compensates the effect of other capacitances connected here, right? C1 and C2, and the voltage drop across R as well. Okay, so now we'll see what would be the not R, only C1 and C2. Okay, so let us find out the first question answer to the first question, that is what would be the value of L and Cm. Okay, and C1 and C2 values are given. Okay, C1 is 0.0018 microfarad, C2 is 0.0186 microfarad. Then the value of L of the tuning inductor can be given by this equation. Already this equation we know this equation is valid for the nominal frequency, right? Valid at nominal frequency. Okay, valid at nominal frequency. Okay, and omega is 2 pi f. By putting the nominal frequency we will find omega here, and substituting omega we'll find L here because C1 and C2 they are given. So L is equal to 496.7 Henry, which is equal to the given value of L. Okay, so is the given value is given. So L we found from that, right? And now Xm is given 1 mega ohm, and Cm has to be in parallel resonance with Xm. So Cm is really compensating Xm. Therefore, we can find Xm by same formula, xm is equal to 1 by omega cm, and from that we can find cm is equal to 3.183 into 10 to the power minus 9 farad. The value is also same as the selected value of cm, hence the selection of both L and cm is appropriate. So cm is it given? Cm, okay, cm is not given, we need to find in fact. Okay, so answer to the question B, that is finding the voltage just by, we know that just by writing this equation. Already we have seen this equation in the previous example. We derived this, V by V2 is equal to C1 plus C2 by C1. Just by substituting this, we'll find V by V2, and V2 we know that is 6.6 kV, and substituting this we'll find it is nothing but 132 by root 3, and the line voltage will be 132 kV. Okay, so this is the answer to question B. Okay, let us see the answer to question C. So already we know that the core loss is given 20 ohm, and just by substituting V2 square by Rm, that is equal to 20 ohm, we'll find Rm, right? So Rm is equal to 2.18 into 10 to the minus 10 to the power 6 ohm. Okay, it's very huge value. In fact, in the transformer, Rm and Xm values are very high. And the VA burden is given here 150 volt ampere. Okay, so now we can find RB from this. V2 square by RB is equal to 150, and V2 we know, and RB will find this RB in fact is nothing but it is transferred to the primary side. So when it is transferred to primary side, it is the value becomes very high, 2.904 into 10 to the power 5 ohm. So it's a very huge value, and it is transferred to the it is in fact the transferred resistance to the primary side, that is 6.6 kV side. Okay, similarly we can find Lm. Lm can be found from Xm, that is 3183.1 hertz, right? 1 Henry, sorry, Henry. And now we can draw the equivalent circuit. The equivalent circuit, if we'll draw with different parameters, now substituting different parameters, and the primary side voltage is 6.6 into 10 to the power 3, that is 6.6 kV. And the C equivalent already we know, C1 plus C2, L we calculated, and the resistance of L is this 4620, right? And Lm is in fact this resistance was not the resistance of the winding, it was not that this resistance in fact includes everything, right? The primary side resistance and the resistance of the inductor. So Lm is 3183 Henry, and Rm is 2.8, already we found Cm, and Rb we found. So by drawing the equivalent circuit, we found this is the equivalent circuit. And now let us modify or simplify this equivalent circuit. By simplifying the equivalent circuit, only we'll have C equivalent RL and the voltage Vt Z. Okay, so the frequency of interest is 47 Hz. So at the 47 Hz, we need to find the phase angle error and the ratio error, right? So hence the value of Xm and other impedances can be calculated at 47 Hz. Okay, so at 47 Hz we need to find Xm and the values of C equivalent, other calculations. After finding this, we can find the Z. Z includes in fact the all the parallel components, the sound components, right? All the sound components are in fact it is there in the Z. So 1 by Z is equal to 1 by Rm minus J by Xm plus J omega Cm plus 1 by Rb, sorry. So out of this we'll find Z. So after finding Z, we can substitute here, and Z in fact calculated at 47 Hz, and also the drop across L and C equivalent, they both are also calculated at 47 Hz, and then we can find the ITH, that is the current through passing through this circuit. So ITH is nothing but VTH is 6.6 K, VTH by R plus J omega L minus J omega C plus Z. Okay, just by substituting the values, we'll find that we'll find ITH, and then from ITH we'll find VT, that is the voltage across the burden. Okay, this is VT. Okay, so we know VTH, which is the voltage fed to the transformer at the primary side, and VTH is the voltage across the burden. Now we can find the ratio error and the phase angle error using these two quantities. So here phase angle error in fact 4.26 degree, because here we can see the voltage VT, which is the angle of the VT is in fact measured with respect to the voltage, because here voltage V, in fact VTH is taken as the reference, that is the voltage fed to the primary side of the transformer. Okay, so that is the 6.6 kV, and that is taken as reference, and VT is making an angle of 4.26 degree with respect to VTH. That means the angle between, if we'll plot VTH and VT here, okay, VT is VT, then VT is making an angle of 4.26 degree. Okay, so that is the phase angle error. In fact, if VTH is fed to the burden directly, there will be no phase angle error, and because of these reactances coming into picture, because of the frequency deviation, we are getting an phase angle error of 4.26 degree. Okay, that is your phase angle error. So now let us find the ratio error, amplitude, or that also known as amplitude error sometime. Okay, so interchangeably we can use these words sometime, please remember. Amplitude or ratio error of CCVT is equal to VTH minus VT by VTH. VTH is your actual voltage, which in fact should be fed to the burden, but actually we are feeding the voltage VT, right? Therefore the difference is the error, and that is the amplitude error or the ratio error, and VTH minus VT. So in order to find the percentage, we need to divide the ideal voltage that should be fed to the burden. So therefore VTH minus VT by VTH in 100, that gives us the percentage ratio error, where VTH is the Thevenin equivalent voltage, that is the ideal voltage, and that is 6.6 kV, and therefore the voltage fed to the burden actually is 6.4, or we can say 6.480 kV, and now just by substituting the values we will find 1.81% is your amplitude error or the ratio error. Now the fourth question was your uh, ratio or amplitude error and phase angle error at the nominal frequency. At the nominal frequency, in fact, only will consider the drop here at the resistance part, right? And then we can find the ratio error and the phase angle error. It is similar to the part C. I hope you can do it. Please do it. Please do the part D. Okay. So next is your assignment 2, and this is 3 questions, and this is all related to VT, voltage transformer, and the date of submission is 4th of September 2020. Please submit this assignment. So thank you very much. We'll stop here, and next class in the lecture 7 we'll continue fault, and we'll not continue, we'll in fact start a new topic, that is fault analysis. Thank you very much. Thank you very much for your kind attention.